We're live.
Excellent. So I just downloaded the paper here. Everyone, thank you for tuning in to Ether Cosmology Reading Night over at Ether Cosmology and also at Space Audits. Tonight, we are going to be reading The Lorentz Transformation Cannot Be Physical by Chan Chu. And this paper, or this author, I just learned about last night. And actually, before we get into the paper, I wanted to read, I wanted to give everybody the same introduction to this guy that I had last night because that was the web page that Alan sent me. Um, Alan, can you drop it in chat possibly?
Oh, yeah, sure. 1 second.
Or you know what? I probably have it in my history here.
Keep talking. I got you.
Yeah. So, yeah, this guy's name is Chan Chu, and I loved what I read, and then I loved even more when I read the bottom of the web page.
In chat now.
Uh, there we go. emc2fails.com. And so, share my screen. I'll just share the whole screen. That'd be easiest. So here we go. About this website. This website is set up in order to publish a very recent discovery by the author that the well known equation E equals mc squared is invalid. In Newtonian mechanics, force is defined using Newton's second law, actually, an axiom, as force equals d over d times t times mv, which reduces to force equals mass times acceleration. Energy in mechanics is defined through the work energy theorem, where work over energy equals the integral of force times distance. In SI units, force would be the unit to Newton and the energy joule. Special relativity attempts to create a new mechanics, a relativistic mechanics, which redefines force as F equals d over dt times mv over the square root of 1 minus v squared over c squared, instead of the simple force equals mass times acceleration, which is used in defining the unit of force, the Newton, in the SI system. It can be easily seen it can easily be seen that there is no way that this new definition of relativistic force could be applied. Sorry, let me zoom in a little bit here because I have bad vision. Well, not really, but applied in any system of units to define a real unit of force. Insisting on this new definition of force renders it only as a mathematical expression, which has no relation to physical reality. Force in relativistic mechanics is only a pure number. As force is fictitious, energy in the integral, force times distance, or the integral force times distance, evaluates only to a pure number without any association with any real physical unit. As the equation E equals mc squared is strictly derived using the work energy theorem, it means that energy in E equals mc squared is fictitious. But the supporters of relativistic mechanics ignore this and just blindly assume that force and energy in relativistic mechanics are still Newton and Joule as in Newtonian mechanics. It could never be. Despite the invalidity of relativistic mechanics based on E equals mc squared, the new mechanics somehow has become the foundation of our modern high energy physics, which includes all of particle physics, the Standard Model, and our nuclear energy theory. This means that much of our modern exotic physics are invalid. They are fictitious and will never bring us any closer to the truth about the physical world, and will never bring any real tangible benefits nor technology that would benefit human society. About the author, Tran Rashid Kaku, from Singapore, year birth 1949, highest education, dropped out first year university, engineering, University of Singapore, 1970. Career, no work history, worked variously at odd jobs factory operator. Email him at here at gmail.com. There you go. So Alan sent me this. I was like, yo, how is this random Chinese GeoCities site like just debunking Einstein straight up? This factory operator. I love this. And then what do you know? This dude
Very passionate about this.
is a bit passionate about this. Yeah. Uh thought I had.
It is
Yeah, I thought I had his full.
Actually, I think I have it.
I definitely, if I reopen enough closed tabs, I'll get
Yep,
there.
yep, I got you.
I got
Sweet.
there. So I so here we go. Here are his papers. He has 26 papers here, I believe, and like they're all pretty in depth. Uh, a lot of them debunking relativity. This was the one I love the title of this one. Proposed water electrolysis experiment may refute mass energy equivalence of E equals mc squared. Or no, where's the one about the here we go. Chemical analysis of plain distilled water may refute mass energy equivalence of E equals mc squared. Like there's so many of these papers I wanted to read tonight. But yeah, so this is all of his papers, and that's about everything that I know about this guy so far. Alan found him from looking into Compton scattering, uh, and he has a couple of papers about that, I believe. But yeah, so tonight though we're gonna read um this here. The Lorentz transformation cannot be physical. And actually, I need just 1 second. All right, sorry about that. So yeah, let's go ahead and dig in. Unless anyone has any thoughts or questions before we do. Cool. So this is from 2017, 14th of June. And let's go through the abstract. The Lorentz transformation will always remain only an abstract mathematical transformation that cannot be incorporated into any theory of physics. The reason being, there is no natural principle that a mathematical transformation carries over association of physical units with any real numbers from the domain space to the image space. Any application of the Lorentz transformation will only result in space and time that have no relation to our physical world. On the other hand, there is no such issue with Galilean transformation, as the orders and clocks calibrated at time zero reads in the same undistorted units at all times. All physical theories founded on the Lorentz transformation are invalid. These include Einstein's special relativity, particle physics, electromagnetism of the Maxwell Heaviside equations. So, the oops.
Is that different from just Maxwell? Maxwell Heaviside?
Yes. Yeah, that's Oliver Heaviside referring to. Do you know anything about that, Alan?
Nope.
Cool. Yeah, I do know that Heaviside would be Oliver Heaviside, which would be much later, or later at least.
Does it have
So
sorry, go ahead.
oh, good. You're all good. So the Lorentz transformation was known before Einstein published his 1905 paper, which introduced his special theory of relativity. In it, he derived the same transformation based on the two postulates of special relativity. The laws of physics are the same in all inertial frames, or in all inertial reference frames, and the speed of light in vacuum is a universal constant. In Newtonian mechanics, the kinematic transformation of coordinates between inertial frames is the Galilean transformation, where speeds may be added or subtracted in the ordinary common sense manner to give a relative speed. Assume an observer moves with speed w with respect to a fixed source of light, and c is the light speed. If this common sense approach is also applied to derive a relative speed of light with respect to the observer, then he would find that the light would have a velocity of c plus w or c minus w. This would mean a violation of the second postulate of special relativity, as the Michelson-Morley experiment of 1887 was interpreted to mean that light has a constant universal speed. It is a law of nature. It was this experiment that encouraged Einstein to propose the universality of the speed of light. To accommodate it, the Galilean transformation had to be replaced. It was replaced by the Lorentz transformation, which is today accepted as the true correct coordinate transformation in agreement with the physical laws of nature. See Figure 1. Assume two inertial frames S prime with origins, or is that prime, right?
Yes.
Yep.
Thank you, sir. S prime with origins O prime, where the frames are similarly oriented and S prime moves with a uniform velocity V in the x direction of S. When the origins O prime coincide, let the times of the frames be T prime equals T equals O, or 0. The Lorentz transform of the frames is given by the following coordinates and time transformations. X prime equals, that's, which one is
Gamma.
that again? Gamma, thank you, sir. And that's not actually an X, is it?
What's that?
Is that an X?
Yeah.
Okay. So we got X prime equals gamma times X minus VT. Y prime equals Y. Z prime equals Z. T prime equals gamma times T minus VX over C squared, where gamma equals 1 over the square root of 1 minus V squared over C squared, C being the constant speed of light. According to the theory of special relativity, an object that has a motion relative to an observer would have its length contracted in the direction of the motion when referenced from the observer's frame. It is supposed to be a true physical phenomena, implying the contraction could somehow be experimentally verified if need be. This contraction could be derived. Yeah, let's give that a little highlight. Yeah,
Oh,
dude, this guy's awesome.
yeah.
Like, I
Look.
already love this paper. This contraction could be derived from this Lorentz transformation as shown below. It is customary to represent a position at a certain point or a certain time as an event in special relativity with a 4 vector combining the position coordinates with the time in the frame as so okay as e time or e x y z t. When dealing with the common Lorentz transformation as an equation 1, we would only use the shortened notation with the x coordinates with t as the event e times t1, t2, e times x1, t1, etc. A rigid rod AB of length L lies stationary on the ground, aligned along the x-axis, the frame of the ground being S. A frame S prime originated or oriented similar to S moves at a uniform speed v relative to S in the x direction. The endpoints of the rod AB are the events A x1 t1 and B x2 t2 in S. We have L equals x2 minus x1. The events of A and B under the Lorentz transformation would become events A prime times x prime 1 t prime 1 and B prime x prime 2 t prime 2 in frame S prime, where x prime 2 equals gamma times x prime x2 minus vt2, x prime 1 equals gamma times x1 minus vt1, t prime 2 equals gamma times t2 minus vx2 over c squared, and t prime 1 equals gamma times t1 minus vx1 over c squared. Let L prime equal x prime 2 minus x prime 1. Thus we have L prime equals gamma L minus gamma V times T2 minus T1. T prime, and then we have equation 5 here, which is showing T prime. So that would be,
It's basically showing how much length would be contracted due to the relative velocity between the stationary observer and the moving observer, and then also corresponding the time as well, because that has to contract proportional so that the speed of light can remain the same. So what we just walked through was just how there's like how the coordinate system changes for the moving observer, right? And it's defined by the gamma factor correction, which is proportional to the velocity times time, or the distance minus time. I'm sorry, the distance minus the velocity times time. There we go. So anyway, that's how it sets it up. It's just talking like we're just walking through what it looks like for, or like what the deviation in time and distance looks like for an observer in motion relative to a stationary observer.
Cool. Thank you. Thank you. So now T2 and T1 in the above equations may be any two random values as they represent the moments of reading off of the coordinates of the ends of the rod AB. The points A and B may be separately read at any time, and their difference will still give the same constant length L of rod AB. We will select T2, T1 in equation 5 such that T prime 2 minus T prime 1 equals 0. In this manner, and from equation 4 and 5, we will get L prime equals delta L minus delta V squared over C squared times x2 minus x1. And L prime equals delta L times 1 minus V squared over C squared. And L prime equals L times the square root of 1 minus V squared over C squared. Now, L prime in equation 6 is the difference in the space coordinates of the two events, A prime and B prime, in frame S prime. Because the times T prime 2 and T prime 1 have been chosen to be the same, L prime has the meaning of the length of the rod AB on the ground as viewed by a stationary observer in S prime at a specific moment, pardon me, in the time of the frame S prime. From equation 6, we can see that if V is greater than C, then L prime is less than L. It is presently well accepted that nothing has been empirically observed to be able to travel faster than the speed of light. So it can be said the relative velocity between inertial frames V can never exceed C. So L prime is less than L is considered a fact of the physical world. Ah, there we go. In our derivation, although it is the observer which is observing the rod stationary on the ground, the convention of special relativity considers the rod to be moving as the observation in frame S prime has to be represented by events B prime and A prime at the same time moment in S prime. This is satisfied as T prime 2 equals T prime 1. And we have here derived the formula for the Lorentz Fitzgerald contraction. Wow. Okay. Yeah. I'm glad you stopped and broke it down when you did. So an object in motion has its length contracted in the direction of its motion. There you go. Despite the fact that special relativity has now been fully accepted as a pillar of modern physics, it will be shown here why it is only an abstract mathematical model unrelated to our empirical physical world. The Lorentz transformation is only abstract. The Lorentz transformation is formally a mathematical linear transformation where the four vectors of the domain space are mapped onto the four vector range space. The four vector components are all pure scalars, in this case, real numbers. Real numbers do not have units. It is only when real numbers are used to represent physical quantities that they have association with real units of measure. So scalar variables or the components of any four vectors are only a pure numbers until there is a proper association of the numbers with real physical measures, in which they have proper association with physical units, such as the SI units of meter, kilogram, or second. We started off with a rigid rod AB on the ground in frame S with length L. L is length in real physical units. This is so only because the rod may actually be physically measured by comparing with a measuring ruler. It is because of this real physical ruler, such as represented by a standard prototype, that L is not just a pure scalar, but has associated with it a physical length unit. Such an association of pure mathematical scalars with physical units is only possible through an implementation of a system of standard measures for a reference frame. Ooh, ooh, whoa, come on there, buddy.
Dude's getting deep with the breakdown. See, this is
Come
really
on there,
interesting because
buddy.
yeah, I've asked some relativists about this, and they're like, "Nah, it's all good. You don't understand." And it's like, nah, clearly there's something meaningful here to
What
this type of
this could be
analysis.
rad, actually. This is pretty good. As all inertial frames are equivalent in classical mechanics, all such frames, such as S and S prime, have implementations of physical length or such as S and S prime have implementations of physical length unit for the respective coordinate systems. But these units for length may theoretically be used only where both the observer and the target object of measure are both fixed, or as under the Galilean transformation, object length does not distort and change. From equation 6, we have L prime equals L times the square root of 1 minus V squared over C squared. So it seems we also have L prime in the same unit of length as associated with L. It may come as a great surprise to many that L prime is not in the unit of length. It is only a pure real number. Let's make that orange. A great part of modern physics theories today are founded on the Lorentz transformation, and it is assumed that all variables in the Lorentz transformation are representing real physical quantities without anyone calling into question if there is any justification for such an assumption. Dude, I didn't think anyone said these things other than us.
Just just some Chinese factory worker or whatever.
Or whatever. Yup. Not one physicist has ever given an explanation why the pure scalars in the image space S prime 2 may take on the same physical units as in the domain space. Man, I'll tell you what, man, I listened to a couple of videos earlier today where they kind of tried and then they kind of admitted they couldn't do it. Anyways,
Couldn't do what?
uh, give an explanation why the pure scalars in the image are two, like how essentially how you can't map the physical units to a domain space, right? Like it's just purely pure numbers. They just assume, I mean, this is like the covariance assumption right here, right? Like that is just assume that all the variables in the Lorentz transformation are representing real physical quantities. But no one ever questions if there's actually an assumption of that or if there's a justification to that.
Oh yeah. No, they can't. Because if you
Yeah.
just yeah.
Yeah. So that's kind of what he's saying. And not one physicist has ever given an explanation why the pure scalars may take on the same physical units as in the domain space. Like it's just like they make that logical jump without. It's like what, some people do when they try to explain weighing, or everyone seems to do when they try to explain weighing.
When you caught that inherited belief system or whatever. And then
Yep.
but the math checks out, right? See, that's the crazy part. It's like
Yep.
you can Lorentz transform and then you can find out that it's covariant with the rest frame. And you're like, oh my God, no way. Time dilation is real.
Yep. Or just use your pseudo tensor and make anything you want reality.
You don't even
Mathematical. What's
have to
that?
know what it means. You can just apply it willy-nilly or have someone else apply it and get you right back to reality. Easiest thing in the world.
Yep. So mathematical mappings only relate abstract objects abstract objects from the domain space to the image space. It is irrelevant in mathematics whether the objects in a mathematical treatment have any physical association. Another fantastic statement. It is only in physics that mathematical objects used must have physical significance, as physical theories deal only with quantities that may be measured and examined experimentally.
Huh.
So when the Lorentz transformation is applied to arrived at L prime equals L times the square root of 1 minus V squared over C squared, any association of L with a physical unit become irrelevant. All the mathematics in the above derivations work only on the pure mathematical object stripped of any association with any of with or any association of any with physical units. So the variable L prime in equation L prime equals L times the square root of 1 minus V squared over C squared is only a pure real number with no association whatsoever to any standard unit of measure. Boom. There is no natural principle that mathematical linear transformations also carry over associations of scalars with real physical units from the domain of to the image space of the transformation. I'm going to read that one more time because it's a little bit dense. There is no natural principle that mathematical linear transformations also carry over associations of scalars with real physical units from the domain to the image space of the transformation. So just you can't, once you step out of reality and you start applying a bunch of math, it doesn't mean that it carries over back to reality, essentially. That's how I gather that. But I'm going to change this one to red. And then we're going to do this yellow. Okay. Length contraction and time dilation are not. I wonder if this is a quote from someone else. I thought it looks like it is, but then he doesn't have it.
Dude's quoting himself, bro.
He's quote himself. Yeah, I think
Dude's
you might be
Kanye West
right.
in it.
Dude, you might be right. All right. So, length contraction and time dilation are not real physical phenomena as taught in the special relativity theory, but are only predictions from its abstract mathematical model, which do not exist in the real physical world. Uh, yeah, I'm just going to highlight it. The paper shows, so conclusion. The paper shows that the Lorentz transformation is only of an accidental historical interest more than 100 years ago when it was found as a way to resolve the impasse presented by the Michelson-Morley experiment. It should not have been incorporated into any physics which deal only with measurable and verifiable quantities. Any application of the Lorentz transformation will only result in space and time that are distorted and which cannot be related to our physical world. Yes, true. All physical theories founded on the Lorentz transformation are therefore invalid. Roger. These include Einstein's special relativity, high energy physics, particle physics, and electromagnetism of the Maxwell Heaviside equations. There you go. Let me
Well, that was a short one.
Yeah, it was.
You want to check out that distilled water paper real quick?
Yeah. Do you want to read that one
Yeah, sure.
or drive to? Maybe.
Yeah. Yeah, let
And
me
actually step away for just a second. I'll be right back.
all right, while you're doing that, I will look for the paper. And of course I didn't download it. All right, just a second. Almost ready, lads.
Yo, I am back. Sorry about that.
Welcome back. All right, had to properly log the old PDF. All right, here we go. Screen share.
Oh, dude, wait.
What's up?
I never streamed.
Oh, no way.
Oh, is
Wow.
that your first time, Toby? Welcome to the party.
Oh,
That's
dude.
insane, dude.
Bro, you totally pulled a Shane there. Good job, bro.
Yeah, well, I guess I'll be mirroring yours.
No worries.
Remember that time when all three of us failed? That was weird.
Yeah. All right. So here we go. This is a chemical analysis of plain distilled water may refute mass energy equivalence of E equals mc squared by Chan by Chan Chu. All right. So 17 December 2019. Abstract. Despite E equals mc squared being the foundational equation of modern physics, it has not been experimentally verified. Though four eminent physicists claimed a direct test of E equals mc squared, quote from Nature 2006, giving verification accurate to 1 to 10 to the 6. The experiment was not any verification of E equals mc squared, but rather an alternative experiment to deduce the mass of a neutron. Classic, dude. Instead of the usual what is it? Instead of the usual what is this word? What are we looking at?
Deuteron? Deuteron interaction?
Yeah, the old deuteron interaction. They use the nuclear interaction involving sulfur 32s and silicone Si. Oh, okay, these must be what do you call it? What's that thing? Periodic table or whatever.
Yeah, chemical
Something.
abbreviations or whatever.
Something or other. Okay, so the claim of the accuracy of 1 to 10 to the 6 is about the comparison of the new value with the accepted values of the mass of the neutron. Nice. This paper shows that the chemical analysis with a good analytical balance of the mass composition of oxygen and hydrogen in plain distilled water may show that the law of conservation of mass is universally valid without the need for the hypothesis of mass energy equivalence. This would also imply an unequivocal refutation to E equals mc squared. Such an experiment could be easily carried out by any laboratory in today's universities. The experiment should be simple and straightforward, and yet its outcome may have enormous consequences for the world of physics. It may be said that the equation E equals mc squared is the most important equation in all of physics. This equation is based on the principle of mass and energy equivalence. It also leads to the energy and momentum equation of relativistic mechanics of E squared equals pc to the second power plus m sub 0 times c squared to the second power, which underlines the foundation of modern high energy physics, including the particle physics of the Standard Model and all of nuclear physics. If these equations fail, then the hypothesis of mass energy equivalence too would be invalidated, and the whole of modern physics would collapse. Such a scenario would be beyond imagination. The equation of E equals mc squared is well known. It seems to be fully accepted, with no one interested ever to raise any doubts about its validity. What is not well known is that the equation has not been experimentally verified. The authors of this paper, which elaborates on this issue, this is despite the four eminent physicists who have claimed to do a direct test of it and measure it with an accuracy of 1 to the 10 to the 6.
I'm not familiar with this one. Are you, Alan?
No, never heard of her.
We
See,
might have to check that one out.
you know what? Skip ahead real quick and look. All right. See.
Direct test. They found it right where they were looking for it.
You don't say.
Nice.
Bill. Oops. All right. So we got that. That's where they've claimed to have measured it.
Sweet.
Second. Which gives an accuracy to 1 to the 10 to the 6. And I think the experiment would by now be an embarrassment to the physicist involved. As for whatever reasons, they misinterpreted the very experiment that they set up. The experiment was never anything. That's a bold claim, dude. He makes bold claims and then he delivers hard.
He delivers
like
hard.
at the beginning of that Compton paper, bro. I was like, dude, this dude is saying some stuff, and he's only got like 2 pages to substantiate it. Like, and then it was just like boom, 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 boom.
Dude, that was the best, like probably the best Lorentz transformation breakdown I've ever read.
Yeah, really
That was
good.
really, really fantastic. And this is so far so good.
Yeah,
I like the way he writes a lot.
Yeah, he's got that Wong attitude, you know.
Yep.
Where he's like, I'm tired of this.
Yeah, agreed.
All right, so they've misinterpreted their own experiment. But did they believe in it or whatever? The experiment was never anything close to the test of E equals mc squared. It was just another experiment to deduce the mass of the neutron, relying on the very principle of mass and energy equivalence. There is an accepted deduced mass of the neutron based on the binding energy involved of the Okay, we're gonna have to look this up.
Deuteron. So this deuteron's pretty important, it sounds like.
Yeah, let's see. Let's get deuteron.
Keep waiting. Every time we get confused about what a deuteron is, I keep waiting for Stone to pop in and like know everything about
All
it.
right, so the deuteron, the nucleus of deuterium, heavy hydrogen. This consists of a proton and has a neutron. The deuterons are formed chiefly by ionizing deuterium. Deuterium, is that right? Deuterium? Stripping the signal electron away from that old single valence electron just waiting to be stripped out.
Mm-hmm.
Yeah, and they use this as projectiles to produce nuclear interactions for accumulating energy of the particle accelerators. The deuteron. I mean, do we call it a deuteron?
Deuteron.
Yeah, the deuteron is a result which was captured by a slow neutron okay, I'm done. I don't care what it is.
Like
I actually don't give a shit. Yeah,
every time I open a geodynamo paper.
Yeah, it's just some interaction that they're claiming is happening on a really tiny scale. Got it. Okay. So
okay. Go back to the beginning of that sentence, maybe.
Yeah, let's see. It was just another experiment to deduce the mass of the neutron, relying on the very principle of energy mass equivalence. There is an accepted deduced mass of the neutron based on the binding energy involving the deuteron. What the new experiment was to use an alternative nuclear interaction instead of the usual deuteron interaction. They used the neutron captured by sulfur and silicon and then deduced that the neutron mass through computations involving the binding energies of what they already assumed of how much everything is and how much charge it has, et cetera, et cetera. So they just hella reified it to infinity. All right. The accuracy obtained is 1 part per million. The accuracy of their new deduced neutron mass was compared to the accepted value. Nothing else about this verifies E equals MC. Jesus, dude. Yeah.
What did we just read? What? Wait, we're gonna have to look at that paper now because that's insane.
So just using the values of what they already assume for the model, right? They just backwards extrapolate what the value would be based on what they measured. So
Well, yeah, right
essentially,
where they were looking for it,
yeah,
accurate to 1 part per million, dude.
yeah. So essentially, going back to the Compton effect, where how they're not measuring the actual wavelength, they're just measuring the ionization. Let's see, the ionization of the X-ray, and then they're like, oh, this must have been caused by a wave, you know, uh, of this wavelength because nothing else could explain blah, 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 right? And it's like literally just measuring an energy fluctuation, and then they reverse engineer what it would weigh based on the model that they made deriving going about all the way back to the electron essentially, where they
It looked like that.
particleized that.
It looked like that other paper was. It's just like it looked like it was like a pretty short little Nature article, so we should definitely check it out like after this or now or whenever.
Yeah, let's see here. It's a 2-pager. Let's crank it out real quick. You want to do it now
I
or?
can You can popcorn me if you want.
All right, yeah, popcorn you in for this, and then we'll tag back in
Okay.
for the thing. Hold on, let me bring it up.
So we're taking a quick little detour from that other paper just to read the paper that he
Oh,
just kind of body bagged. So, direct test of energy equals mass times the speed of light squared. One of the most striking predictions of Einstein's special theory of relativity is also perhaps the best known formula in all of science. Energy equals mass times the speed of light squared. If this equation were found to be even slightly incorrect, the impact would be enormous, given the degree to which the special relativity is woven into the theoretical fabric of modern physics and into everyday applications such as GPS systems. Here, we test this mass energy relationship directly by combining very accurate measurements of atomic mass difference, delta M, and of gamma ray wavelengths to deduce E, the nuclear binding energy for isotopes of silicon and sulfur. Einstein's relationship is separately confirmed in two tests, which yield a combined result of 1 minus, is that 1 or is it I? 1 minus delta mc squared over E equals negative 1.4 plus or minus 4.4 times 10 to the negative 7, indicating that it holds a level of at least 0.00004% to our knowledge. This is the most precise, direct test of the most famous equation yet described. Pat ourselves on the back. Our direct test is based on the prediction. Wait. Okay, so our direct test is based on the prediction. Okay. That when a nucleus captures a neutron and emits a gamma ray, the mass difference, delta M, between the initial, including unbound neutron, and final nuclear states, multiplied by c squared, where c is the speed of light, should equal the energy of the emitted gamma rays, as determined from Planck's relation E equals hf, where h is Planck's constant and f is frequency. The total energy of the gamma rays emitted as the daughter nucleus decays to the ground state was determined by summing the individual gamma ray energies. I'm going to read that one more time. The total energy of the gamma rays emitted as the daughter nucleus decays to the ground state was determined by summing the individual gamma ray energies. Okay. These were obtained by a wavelength measurement using crystal Bragg spectroscopy. The mass difference, delta M, is measured by simultaneous comparisons of the cyclotron frequencies, inversely proportional to the mass of ions and the initial and final isotopes confined over a period of weeks in a penning trap. For an atom X with a mass number of A, look at that guy, Albert, father of the famous formula. So yeah, back up. Undergoing this nuclear reaction, the comparison is expressed in terms of measured quantities as delta MC squared equals M to
Otherwise known as equation 1.
yeah, let's go with that. I was determined. I'm like, I want to read this. I'm gonna crank through this, and I'm like, oh, don't even know how to read that. I don't even know what is. Okay, I don't know what's going on there with the symbol before the X. What is that? Or is
Let's
that
see.
the M to the power of A?
This right here?
Yeah.
Yeah, I have no idea, brother.
Okay. Maybe he'll explain. So, where the Avogadro constant N A relates the measured mass measured mass mx in unified atomic mass units AMU, its mass its mass in kilograms mx. We made comparisons for x equals si so a plus 1 x equals si and a plus 1 x equals s. The mass of the neutron Mn is determined from the masses of hydrogen and deuterium. Wait, so what? I thought we were talking about silicon and is this where like they? Because I thought we were talking about silicon and a different element, and then now he says hydrogen and deuterium. But what do they say? Anyways, combined with FD, the frequency of the gamma ray corresponding to the deuteron binding energy. The molar Planck constant is NaH equals 3.990312711627 times 10 to the negative 10 JS or J small to the negative 1. Numbers in parentheses indicate uncertainty on the last digits. The figure has been independently confirmed at about 5 times 10 to the negative 8 level by a range of experiments through its relationship with the fine structure constant. Citation 1. Its relationship, a level of experiments through its relationship with the fine structure constant. Okay. The gamma ray frequencies on the right-hand side of the equation 1 have been measured using the GAMS-4 crystal diffraction facility at the Lou Levant Institute in Grenoble. The gamma rays emitted from the sources located near the high flux reactor core are diffracted by 2 nearly perfect flat crystals whose lattice spacing d has been determined in meters. The diffraction angles, uh, what's that called again? Theta, thank you. The diffraction angles theta are measured with angle interferometers calibrated using a precision optical polygon, figure 1a. The wavelengths are determined from the Bragg equation, delta equals 2d sine, and were measured for the 3.5 MeV and 4.9 MeV transitions in Si, or silicon, for the 0.8 minus MeV, 2.4 minus MeV, and 5.4 minus MeV transitions in S, and the 2.2 MeV transition in deuterium. H. See supplementary information. Because the diffraction angle for a 5 MeV gamma ray by a low order silicon reflection is less than 0.1 degree, our binding energy determinations were limited by our ability to measure the diffraction angles of the highest energy gamma rays. Our binding energy determinations were limited by our ability. Okay. With fractional accuracy better than about, go ahead and scroll down, a tower 10 to the negative 7, a slightly revised value of FD from that given in reference to is also reported here. See his exact, a bunch of values for FSI, FS, and FD. These values of FSI and FS are respectively 25 and 50 times more precise than earlier values. Oh, that sure looks like a lot of numbers, so must be real. The mass difference was determined by direct comparison of the cyclotron frequencies of 2 different ions simultaneously confined in a penning trap. We're probably gonna have to look up this penning trap thing. I don't know how much time we really want to spend on this, but it's like the second time they've referenced this penning trap, and I have no idea what it is.
Look it up on the side.
Cool. So the mass, I'm going to read that paragraph again. The mass difference was determined by a direct comparison of the cyclotron frequencies of two different ions simultaneously combined in a penning trap. It must be some way that they claim to measure, something they measure the energy of an electron from.
So a penning trap is a device for storage of charged particles using a homogeneous magnetic field and a quadrupole electric field. It is mostly found in physics and science and related fields of study as a tool for precision measurements of the properties of ions and stable subatomic particles.
Wow. Okay, so it's like a suspending magnetic field
Yeah,
for
I wonder
particles.
if there's any. Get a. Okay, here we go.
Pretty
Yeah,
interesting.
here we go. So this would be. That looks. The
Wow.
old penning trap, eh? Let's see, we got the fluorescence, the captured ion cloud, correction electrode, end cap, segmented ring, incoming
You go pull your fingers
ions,
out.
and a laser beam. So what is it? Just what is it? What did we say? It was measuring the ionization, turning it into energy or whatever.
Yeah, so I guess that's how they're saying that they're measuring
Oh
the
yeah,
old mass energy equivalence.
yeah. So so this is basically the same thing that they do for the content effect, essentially.
Gotcha. Okay.
Yeah, when he's talking about like it's not a direct measurement of it, like they're just calculating it off based off of what they already assumed, and the comparison
Yeah,
to
they're using
the
cyclotron frequencies. So now let's look up cyclotron frequencies too then,
and
unless you're
the
familiar
nope,
already.
never met
'Cause,
her.
yeah, you would have to like hmm. Yeah, I don't
So,
know. I would be curious to know how they can make these assertions based on a frequency,
let's
make
see
assertions about
here.
mass.
Oops, it's cyclotron resonance. Okay. Cyclotron resonance describes an interaction of external forces with charged particles experiencing a magnetic field, thus already moving in a circular path. It is named a cyclotron for the cyclic particle accelerator, but while the oscillating electric field adds kinetic energy to the charged particles.
Hmm.
Yeah. So let's see, cyclotron. We'll do one more. All right. Cyclotron. The cyclotron was the earliest type of particle accelerators. It is still used at the first stage of some large multi-stage particle accelerators. It uses the magnetic force to move charged particles and bend moving charges into semicircular paths between accelerations applied by an electric field. Okay. So it was basically a way for them to keep a charged particle like in a loop essentially without interacting with anything. I don't know. What it kind of sounds like
Yeah,
they're
and then somehow they're able to measure like there's a frequency that they get out of that. So it must be the frequency of the way that it moves in that field.
yeah, it sounds like it's just affecting the oscillation rate of what's inside of there.
Okay, and so then because of that, they say that they can then deduce the mass and energy of that from wow. Wait, so the mass specifically. Okay.
Yeah, because
But
they're
it's
gonna reverse engineer the output of that and then turn it into they're gonna go, okay, well what would the kinetic energy be? Okay, how much mass would you have to be how much charge would you have to be carrying for that little tiny mass to produce, like, you know what I'm saying? So like they'll just walk it back like that. And that's what he's calling out in this paper.
gotcha.
That this isn't a measurement of the equivalence. This is just you guys measuring energy fluctuations again and using it to reify your entire model and story about a particle interaction on the subatomic level.
Cool. So yeah, let's just jump Let's finish that paragraph. Where were we?
Right here at the pinning traps there.
Yeah. So yeah. Oh yeah. Thank you. So this 2-ion technique achieves mass comparisons with fractional accuracies below 10, 10 to the negative 11. Well, yeah, once you compute it, sure. By virtually eliminating the effect of many sources of noise, such as magnetic field fluctuations. During measurements, the two ions are placed on a common circular orbit, magnetron mode, on opposite sides of the center of the trap. Okay. And separated by distance of about 1 millimeter. Figure 1b shows that the measured cyclotron frequency ratio is almost completely independent of ion-ion separation, tightly constraining the size of the largest possible systematic errors. The ion mass ratios reported here, namely this value and this value, are respectively more than 700 and 100 times more precise than previously known. Citation 6. The total uncertainties include the uncorrelated uncertainties of 4 times 10 to the negative 12, each from ion-ion interactions, trap field imperfections, and statistics. Okay. The ratios also include corrections of 45 times 5 times 10 to the negative 12 and 7.3 times 2 times 10 to the negative 12 to account what? Okay. To account for polarization induced shifts of the cyclotron frequencies. What? Okay. See methods in supplementary information. After accounting for the mass of missing electron and chemical binding energies, the ion mass ratios give the neutral mass differences that ms plus mh minus ms. Yeah, that value AMU, and then another value of AMU. And by the addition of MD minus 2MH equals another value of MU. To each one, we obtain the desired mass differences of equation 1, with a fractional accuracy of that old 7 times 10 to the negative 8 for both. Comparing the measured energies and masses, we report two independent tests of E equals mc squared. The two comparisons find a measured fractional difference between E and delta MC of 2.1 times 5.2 times 10 to the negative 7 and negative 9.7 times 8 times 10 to the negative 7 with sulfur and silicon isotopes, respectively, and a combined value of negative 1.4 times 4.4 times 10 to the negative 7. The error on this comparison is currently dominated by the uncertainty of the gamma ray measurements. This result is 55 times more accurate than the previous best direct test of E equals mc squared, which was performed by comparing the electron and positron masses to the energy released in their annihilation. Oh, that's another one we'll have to check out someday in another, 7 years when I'm interested again.
Oh, dude, you want to know about photon energy annihilation, dude? We could hit up Franco. He knows a lot about
Oh, our
photon.
boy.
He knows a lot about electron annihilation.
Yeah, Franco's
You
deep
have
in
to
that
talk
mute
to
list
him,
these
though.
days.
So like
What's
I
up?
don't get okay. If you annihilate a particle, what does that actually mean?
It means that when you do it algebraically, you remove the virtual particle that you invoke to reify the physical phenomenon. Probably. That'd be my guess.
Annihilate a particle, bro. Freaking
So I can keep reading from here for a little bit.
Oh yeah, dude, I totally blacked out and forgot we were on this one. Okay,
Yeah, let's
so
get back to the good paper.
yeah, dude,
You know, I
read a
purposely
bunch
tried to like read fast through the end of that because I was like, all right, we get it.
read a bunch of disgusting filth or whatever. Just kidding. All right.
So
This-
I'm going to read the highlighted part again since we went back and read the paper. Accuracy obtained of 1 part per million is the accuracy of their new deduced neutron mass as compared to that of the accepted value. Nothing at all about verifying E equals mc squared accurate to 1 part per million. The current situation is that Einstein's special relativity and E equals mc squared have been fully incorporated into modern physics despite the equation being not experimentally verified. This issue should be of the utmost of concern to the physics community. A revival of law of mass conservation would refute E equals mc squared. In the 19th century, the early chemists who studied the chemical composition of compounds found some patterns regarding the atomic mass of the elements. Atoms have masses that are close to the whole numbers as compared to the atomic mass of hydrogen. English chemist William Prout in 1815 and 1816 published papers that proposed that Prout's hypothesis. Does anyone know if I'm saying that right?
Who's that? Prout's
Prout?
hypothesis?
Yeah,
I mean, you're not saying it, right?
got it. The English chemist William Prout in 1815 and 1816 published papers that proposed that Prout's hypothesis elements are composed of whole numbers of atomic hydrogen as the basic constituent. This imply that the atomic mass of elements would be whole numbers as measured in our current unified atomic mass units. This would be consistent with the law of mass conservation that mass cannot be created nor destroyed. That's interesting. All these changed after Einstein introduced special relativity in 1906, which led to the equation E equals mc squared and the principle of mass energy equivalence. The notion of mass energy equivalence eventually gained full acceptance. This happened after the invention of mass spectrometry, which became the principal technique to measure atomic mass by replacing the traditional chemical method using the scale balance. Today, for whatever reasons, chemical method to measure atomic mass has been totally abandoned. Ooh, that's interesting. All these mass spectrometry. So that's those first little mini particle accelerators, the old what was it called? The frequency thing. That thing we just looked up. The heck, I can't think of what it's called. Cyclotron.
Cyclotron, there you
It
go.
was measuring cyclotron frequencies using the penning trap or whatever. Oh yeah, there you go. He says it right there, penning trap. The author in this paper has shown that mass spectrometry cannot measure atomic mass accurately. Wow. The U.S. National Institute of Standards and Technology database of atomic masses are all measured experimentally with the penning trap, an instrument based on mass spectrometry. The penning trap is touted as a most advanced instrument capable of the highest precision ever for measurement of atomic mass. It is claimed to a precision as high as 1 to 10 of the negative, or 10 to the times 10, or 10 to the 10th power. Blech. But precision is not the same as accuracy. Interesting. Yeah. I guess
Yeah, you know that.
that's a good point.
Accuracy is precise over and over and over again.
Well, precision and accuracy. Like you could be precise, but then not have an accurate value.
Yeah, precision is how many decimal points it goes to. Accuracy is like how correct it is.
Yes. Thank you. So the penning trap is designed based on the Lorentz magnetic force law, and it assumes that the law is an exact mathematical relation, which it is not. Okay.
Did not know that.
Gotcha. The Lorentz magnetic force law is only an approximate law. What mass measurements which the penning trap gives are not true atomic mass, but approximate predictions of atomic mass based on the Lorentz magnetic force. The measurements made would differ by a slight amount from the mass number of an atom, a whole number. This slight difference in mass came to accepted to be correct and was referred to as mass defects of atoms.
What? Dude, what?
What? What's the citation? We gotta
We
pull
may
the
have lost
citation
Toby
on
for the
that,
evening,
dude.
guys.
There's no citation
gotta
for
pull
it,
the
but we
citation
are
on
going
that
to
dude's
look up.
insanity.
We are going to look.
Like,
oh wait,
no, it's not that our measurement could possibly be wrong using this new method. Like, it's just that the atoms are defective. That's so bad. Okay.
The atom's just defective. We're just measuring defective atoms, bro.
Everything's the atomic mass is all
Hey,
real.
yo, dog, get the
Everything is
intern in here.
exact.
Bring me some new atoms. These are defective.
Oh yeah. Oh, open the box behind Jim. That's right.
Rutherford Bohr model.
It is these mass defects which is the cause of violation of mass conservation in nuclear interactions. Mass could be lost in nuclear interactions. Oh. The huge amount of energy released in nuclear fission was then ascribed to the conversion of the mass loss to energy using the equation E equals mc squared. The with mass energy equivalence being fully accepted, the law of conservation of mass was deemed to have been refuted. In its place, the conservation law has been extended to a law of mass energy conservation. The author has a paper, citation 4, which argues that mass conservation without mass energy equivalence is the correct universal conservation law. Mass conservation without mass energy equivalence is the correct universal conservation law.
Yeah, and you know what? Quick side note: Einstein completely agreed with him. He tried to walk back, the E equals mc squared thing, and say, can we just treat mass and momentum separately? Can we go back to that?
Sometime around the 20s or something.
Are you talking
No,
about
it
when
was in the
are you talking
40s.
about when he
Oh,
tried
gotcha.
to redo the proper derivation of general relativity, Alan?
No, that was when he tried to properly derive E equals mc squared as a effect of special relativity, and he couldn't do it. So this is 1948. He wrote a letter to Lincoln Barnett, saying, "Hey, can we go back to regular rest mass and then use the capital M as a momentum?" So
Wow.
Mass conservation and mass energy equivalence are mutually contradictory. Only one of them could be valid, not both. This fact could be
It's
used in
weird he should.
experiments.
Dude, isn't it funny how
Sorry, man.
Einstein literally like had every side and everything, like pro ether, anti ether, like every single one of his own theories. He later on was like, "Yeah, you guys, they just used me. Like the stuff's not real."
just a straight puppet. Yeah.
Man, it's using distilled water right here, bro, and talking about the atomic mass defect in
Yep.
water.
Yep, that's dude. Or is that you're talking about the Chan Chu paper?
2.1 that you're looking at right now.
He has a whole paper about it.
Yeah, but I'm talking about it was on your screen already.
Yeah, we just hadn't read that part yet. Let's see. Mass defect. Here we go. Let's see what the chem labs have to say about it. Mass defect. To the defect.
Control F defect.
Yeah. I was thinking
No,
of
but
that.
it was showing it right there, talking about like the little rounded off decimal points off of the oxygen and the hydrogen in the water. There you go, the atomic mass units. That's why the periodic table, if you look at it now, like the atomic mass of the elements is always like 0.9999 or 0.001 or something like that, atomic mass units.
So those are just those defected
Dude, wait a second.
atoms or whatever?
The measuring device that measures this, doesn't it like isn't it based on it's spectroscopy, right?
Yeah,
Yeah.
that's what we were just looking at. It
They're
uses
shooting
those
waves.
frequencies, cyclotron frequencies.
Yeah, so they're shooting frequencies through matter. So it's like, couldn't like the fact that the wave is traveling through matter and there could be some kind of like dispersive effects cause like a 0.001%, error or something.
That
I
makes
mean,
sense.
Not
Yeah.
only that, but there's the decay of the radiation that's produced also contributes to the electric signal that they measure. They're just converting all of this to electric signals.
If the atomic masses as given in the NIST tables are correct, measured using the pinning trap, then a chemical analysis of the mass ratio of O over H. Can you scroll down?
Well, yeah. Well, hold on. Let's read it.
Yeah, dude,
Where were
Pizio's
we at?
jumping ahead. Dude, God dang it,
Yeah,
Pizio.
dude, you're trying to tell us to scroll down.
Stick with the class, bro. What the hell?
Yeah,
Dang.
stick with the class, bro. So yeah, where were we? We were at that paragraph right in the middle there, right? It is difficult.
Yeah, I think we were right about here.
Okay.
Conservation equivalence and mutually contradictory. Yeah, right here.
So it is difficult to directly verify the validity of E equals mc squared, but we know that mass energy equivalence is, as implied by the equation, means a refutation of the law of mass conservation. Mass conservation and mass energy equivalence are mutually contradictory. Only one of them could be valid, not both. This fact could be used in experiments designed to investigate the validity of E equals mc squared. Mass ratio of oxygen, hydrogen, and water. Water has the formula H2O. If water is formed from the isotopes O and H, the mass ratio of OH in this water could be found by chemical analysis of the mass composition. The atomic masses of O and H, as found in the 2012 NIST tables, are 15.99, blah, 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 and 1.007, more digits. The value or the figures in the brackets represent the error in the last digits. If the atomic masses are given in the NIST tables are correct, measured using the Penning trap, then a chemical analysis of the mass ratio of O over O and H should give a value consistent with the values above. The analytical balances of today are capable of measuring mass with an accuracy of 1 to 10 times 10 1 to 10 to the power of 5 for some mass range. If the NIST masses are correct, then the experiment should give a figure of about that for accuracy of 1 to the 10 to the fifth. If the law of mass conservation is correct, is the correct universal conservation law, then the atomic mass of any nucleide or any nuclide is simply its mass number in unified atomic unit, a whole number. There's not even a need to do any measurement for atomic mass. In this case, the analysis of the mass composition of the water as above should give a figure of about 16 exactly. So the experimental result of the experiment as above would give either one of those two values. 15.870 to a high level precision to 15 to a bunch of digits, or 16 straight up. Without fail, in a good analytical balance could easily distinguish between the two values, which could have a relatively huge difference of 0.12928. If the experimental result gives the ratio of OH to be 16, it would be an unequivocal verification that the law of mass conservation is correct. As mass conservation and mass energy equivalence are mutually contradictory, it would mean an unequivocal refutation of mass energy equivalence in the equation E equals mc squared. On the other hand, if the resulting figure were to be 15.8702 or 87072, it would be a clear refutation of the law of mass conservation. In this case, the experiment would be a validation of the NIST values of atomic masses for precision of 1 to the 10 to the fifth. This experimental result would still not be an experimental verification of the equation E equals mc squared. The equation would still remain unverified. Although the above experiment is for chemical analysis of water formed from pure isotopes of O and H, using plain distilled water would not make any difference to the experiment. Oxygen in nature has three stable isotopes: 99.76, 0.04, and zero point 0.2. For hydrogen, it has two stable isotopes: 99.98 and deuterium, which is 0.02%. We may assume that ordinary water has the pure isotope O, and hydrogen having the natural composition of H, 99.98%, and deuterium 0.02%. The OH ratio for this would be 16 over 1 times 0.9998 plus 2 times 0.0002, or 15.99680. The difference between 16 and 15.99680 is insignificant for the purpose of our experiment. I wonder if someone has something to say about that. Physics experiments of today often require funding going into the millions of dollars and even billions for some major experiments. The chemical analysis of still distilled water to determine oxygen and hydrogen composition by using mass and using an analytical balance should be a fairly straightforward experiment. Most laboratories in today's universities would not have a difficulty perform such a simple experiment. A simplest of experiment by today's standards, yet one which may have an outcome with enormous consequences in a world of physics.
Hmm.
Boom.
So he's
Dude,
like, you can spend billions of dollars and invoke a bunch of like PhD scientists to do all this Einsteinian garbage, or you could just have somebody look at some water on a scale.
basically, yeah. I forgot we were even reading that paper, but he laid it out so perfectly.
Can you drop that paper that just got finished reading?
Mhm.
Absolutely. Dude,
And
you're
you're
gonna
right,
wanna
they
just
do have
go
some
to his
extended
author
time.
page and just grab all his papers.
That too.
What? You're back,
Yes,
Stone?
that is yeah, I'm back, and thanks for finally picking on so I can hear you guys speaking. That's great. Yeah, the same thing you can expect me to say is that it is absolutely preposterous to suggest that any of their measurement mechanisms are accurate to the what is that going to be 100 millionth of an atomic mass?
No, it was more than
Get
that. It was
out of
more than that.
here. It
It
was
was one.
11th decimal point. It was the 11th decimal point. I made a point of anally counting that. It's 100 millionth of an atomic mass. Like, what the living fuck are they talking about?
I was wondering if you were there.
Why do they
Mm.
do that, Stone? Just to dazzle people or what?
It is exactly why they do it. Oh, we are so goddamn precise. How could you possibly argue with anything to do about our data? It's how rat's ass tight our measurements are.
Oh, dude.
It's a
Yeah, that's
lie.
it. They hide it in that, or they use that as the shield.
Well,
Yeah.
yeah, they wouldn't have even like they wouldn't have been able to make that Nature article if they weren't making those assertions. Like that's how they were able that's what the whole point of that Nature article was to dazzle us with their E equals MC squared to this insane degree of precision.
Oh, because yeah, they're gonna be like, we're accurate down to 11 decimal points. Are you gonna make the outrageous claim that we're off by like 0.18?
That
Yep.
they're off at all.
Yeah, exactly. Are we getting into a third one here? Or are we just binging them tonight?
So I was
Can you
gonna,
drop the other one real quick?
yeah, I was gonna say we've been live for an hour, but we could definitely do another one. Like these are pretty smooth reads. What was it? Chemical analysis paper.
They're
What?
awesome.
How do they?
I love how short they are. They're just right to the point, super concise, point made.
What is a scale balance chemical analysis?
Good question.
Because I mean, I learned that in chemistry class that they used to think that everything was like whole numbers of atomic mass units, and actually like he was pretty close. It's really really close to whole numbers, but it's ever so slightly not. Right? That's like what we learn.
Yeah, you just have
So
that defective mass, bro. That's all it is.
I never knew that they said that the atoms are defective. Like that
Yeah.
is bro, the atoms are it's
It was
not that we're not measuring it
Oh, this
correctly,
is a
just
whole paper about it. Yeah, we gotta read this.
Yeah, I was gonna say it's right on
their
topic with mass spectroscopy or
ultimate
Yeah.
spectrometry.
scientific
So
arrogance.
wait,
this
the
is
other one was 2017 or 2019?
17,
yeah,
I think. Oh
19.
wait, I actually don't know.
who knows? Um let's see here. Yeah. Yeah, this is the backbone of a lot of stuff for their model, or like the interpretation of light and how it works. So yeah, we should definitely get in there.
Cool.
All right.
I can start.
Okay. Not gonna fight you on it.
Mass spec What's that? Okay, yes.
Sodium fluoride, bro, is the key. Go ahead. I'm gonna go make some food.
Mass spectrometry measures atomic masses giving precision of 10 to the negative 10, but its accuracy has not been verified. Precision and accuracy are two independent aspects. The Lorentz force law underlying mass spectrometry has not been verified. In the 1920s, the atomic masses of some elements measured through the early mass spectrometers showed some discrepancies from the whole number rule of atomic weights. The physics community accept the discrepancies from the whole number units to be from the whole numbers to be correct. They proposed the concept of mass defects. This, together with the mass energy equivalence of E equals mc squared, allowed old Arthur Eddington to propose a new subatomic energy to account for the source of the energy of the sun to be in line with the 15 billion age of the sun in their theory. They never
So he's to
entertained.
blame. Eddington is to blame. This whole subatomic thing. I pin it on him right there.
Wow, yeah, that would be
Dude,
it right there, huh?
I'm good with blaming Eddington.
Sorry, man.
Yeah, I thought
Yeah,
you
Sorry,
were
I just sensed
for
the
sure.
irony in that one. Yeah.
Yeah.
yeah. When Eddington pops in like that, yeah, that makes
Oh,
sense.
oh, Eddington, you mean the guy that single-handedly pushed general relativity to the forefront and made everyone believe in it with photographic plates that, are completely missing to history? Talking about that guy?
Dude really had a lot of
Yeah, fuck that guy. You're right.
Lot of
someone
inf-
very powerful liked him
yeah.
or wanted to use
Or
him.
or rather he was a part of a powerful organization known as the Royal Society,
Yeah, yeah,
and those
probably.
guys wanted to use them. But yeah.
So yeah, Arthur Eddington proposed a new subatomic energy to account for the source of the energy of the sun to be in line with the 15 billion age of the sun in their theory.
Oh,
They never
Jesus.
entered. Yep.
Yeah.
They never entered.
Shout
Dude, this
out to
guy, I
Eddington.
love the way this guy writes. They never entertained the other simpler option that their mass spectrometers were only approximately good. I mean, that's insane. If the atomic masses if the atomic masses of nuclides were to be just whole numbers equal to the mass number in the atomic mass unit, it would be a confirmation of the law of mass conservation in the atomic and subatomic world. That's so nuts. Dude, that's insanity.
If it just worked out with the whole numbers without the defects.
They're just like, oh, here we go.
That's
Just start using this new tool.
s-
Forget and then
prove it that that's the smallest grain of sand that there is.
So if the atomic masses of nuclides were to be just whole numbers equal to the mass number in atomic mass unit, it would be a confirmation of the law of mass conservation in the atomic and subatomic world. The key to decide the fate of the nuclear physics in sodium fluoride NaF, sodium and fluoride or fluorine occur in nature only as single stable isotopes. A chemical analysis of NaF with the current analytical balance to determine the relative atomic mass of Na/F would decide conclusively if mass spectrometry is accurate. The current relative atomic mass of NaF is 22.9897 or 769 slash 18.998403 or 1.210089. The ratio of the mass number of NaF is 23 to 19 or 1.210526. Accuracy of mass spectrometry would be confirmed if the value is 1.210089 plus or minus that. Otherwise, if the value is 1.210562 plus or minus 0.00012, it would mean a confirmation of the law of conservation of mass. Okay. The implications of such a scenario is beyond imagination. The whole world of nuclear physics would collapse. Introduction. Despite the very great advancement in physics since the time of Newton, there are some basic physical concepts that have not changed. One is the concept of mass. It is still the same quantity of matter in Newton's Principia. Even special relativity cannot run away from this. From this concept, as when a relativistic mass come to rest. Can you scroll back up real quick?
Yeah, this is super important.
This is kind of like reads funny.
So
Even special.
yeah.
Here we go. Okay. I get it now. Even special relativity cannot run away from this concept, as when a relativistic mass come to rest, it would still be the same invariant mass of Newton. We are here concerned only with mass as quantity of matter. The measurement of mass is central to physics, as mass is one of the basic dimensions of physical nature upon which the science of physics is based on. There cannot be the least of a compromise concerning the measurements of mass if physics is to be sound as a science verifiable through empirical and experimental evidence. The method to measure amount of substance since antiquity is the weighing scale based on the lever principle. Although we now have a formal name for the principle as Archimedes' lever principle, the ancients, not just the Greeks, just understood that was the way to correctly weigh and measure gold, silver, grains, etc. It was just an obvious empirical principle. So the weighing scale for mass is a direct method to measure quantity of substance and matter. We
You-
say it is direct as it is based only on a universally recognized natural principle. The balance scale was so much trusted that the sacred texts of some religions seem to suggest that the scale was so accurate it could even measure the amount of sins that a man committed while living in the world. In the early days of chemistry, compounds were analyzed to unravel the compositions of pure elements within a compound. To unravel the compositions of pure elements with a compound. From such analysis, together with the development of molecular theory, the atomic weights of atoms could be calculated. An English chemist, William Prout, in 1815 found that the atoms of elements all seem to have a mass that are whole numbers of the mass of the hydrogen atom. The so-called whole number rule of atomic weights, known as Prout's hypothesis or Prout's hypothesis. So they have a scale of atomic weights of the elements, with the hydrogen atom being 1. In this scale, the atomic weight of oxygen is 16, nitrogen 14. In fact, some of the earlier periodic tables had atomic weights of the elements as whole numbers. This whole number rule appeared to be discredited when mass spectrometry was invented in the late 1910s. Mass spectrometers could sort and isolate ions of nuclides and weigh them with the new scale of the 20th century to higher and even higher resolution until they found that the atomic weight of an atom differs slightly from the whole number, which is the mass number of the atom, the number of protons and neutrons. It was with mass spectrometry that the isotopes of elements were discovered. Isotopes are different nuclides of the same element with different atomic weights. With his first spectrograph, J.J. Thomson in 1913 found that neon had two species, the Ne20 with the usual atomic weight of 20 and another with an estimated weight of 22. This was the start of the discovery that most elements in nature have more than one isotopes. Many have stable radioactive isotopes or non-radioactive isotopes, with their abundance distribution being rather fixed for many of the elements. Following this would be a new age of nuclear physics, as the ability to even weigh the mass of nuclides would allow for greater understanding of the atom and its nucleus. In fact, this ability to weigh an atom borders on the miraculous and seems to infringe on a domain that once were reserved for the gods. With this new technique of mass spectrometry, the push was for higher and yet higher resolution. The latest mass spectrometer using the Penning trap has the ability to weigh ions to 1 part in 1 to the 10th power, or one part in 10 to the power of 11. The physics world only cared for greater resolutions of their new tool. No one stopped to ask the critical question: is mass spectrometry accurate? The main aim of this paper is to answer this question. Popcorn, whoever. Alan, I
Yo,
guess.
if you
And
could
it's
give
1 part in 100 billion, by the way.
if you could give me like 2 more minutes of reading, I got you.
You got it.
All right, thank you, sir. Sorry about that.
All good. Before we question the accuracy of mass spectrometry, we will first examine the question of reliability of a method for weighing mass. Here we are questioning whether the principle behind the method is accurate. Take the common scale balance that have been used since antiquity. Is the principle of such a balance reliable? The answer is a resounding yes. The scale is based on a universally accepted natural principle. As we have noted earlier, the scale is based on the lever principle, may even be said to be a direct method of weighing mass. It is the only direct method of weighing mass among the available types of weighing balances. All other types of weighing scales may be said to weigh mass indirectly, as they have to rely on the properties of some physical phenomena in order to determine the mass of a body. If the physics behind the method is not accurate, then the weighing scale would not be accurate. Let's examine the simple spring balance. It relies on the extension x of a spring from its equilibrium position, where the extension is proportional to the force pulling on the spring. F equals mg equals kx, where k is the spring constant. The equation simplifies to m equals k over g x or times x. We could just use one calibration of x1 with a standard weight m1 and simply use this reference mark to calibrate the spring balance to read a whole range of weights through simple proportionality. Every equal division between two markings represent the same change in the mass reading. Is this spring balance reliable? We all know that it is not. The principle behind this balance is appropriate as we know the linearity of any spring is only approximate within a range of extension. This shows that any method that weighs mass indirectly has to be verified. What was that bold thing? You can go back up real quick. Uh, it always, it always, it is always necessary to verify the accuracy of a method to weigh mass if the method is incorrect. Yes, that
I
makes
could
sense.
I could take over now.
Okay.
There we go. The most precise chemical balance today is the analytical balance, the force restoration balance. When a weight is placed on a scale pan, it will tilt a balance beam. There is a sensor that detects the displacement. An electromagnet restoring force is applied at the other end through a transducer circuit until the beam's tilt is neutralized. The transducer will record the current needed to produce the restoration force. That's cool. Such a transducer has been tested for linearity that the force is proportional to the current to a high degree of accuracy. The current would need to be translated the current would now be translated to a weight measurement. The analytical balances today are capable of an accuracy to weigh a gram to 1 part in 10 to the 5 or 10 to the 7. So high degree of precision. Let's see. Besides a direct experimental verification of the principle behind the balance type, there are 2 physical tests that are available that may be used as indirect tests of the principle behind the balance. These 2 tests could also detect flaws in the individual balance due to design or technical failure. 1. Consistency test. The balance may be tested to be consistent with a different but verified weighing method. As an example, the analytical balance can be tested for consistency with a balance beam. We know that the beam balance has a much lower precision, but by comparing the 2 balances to weighing a sample, the analytical balance's readings must be consistent with the beam balance's readings in order for readings for its order of uncertainties. Such a consistency test is fundamental, and balance type should never fail such a test. Linearity test. A balance weighs the sample A and B separately, giving the values MA and MB. When it weighs A and B together, the results combined of the masses A and B must be equal to the assigned values MA plus MB. All right, so the general principles of mass spectrometry. Man,
Yeah, it's like you're so
dude,
used to saying spectroscopy that it like throws you off. It's spectrometry.
spectrometry.
Think spectrography.
Oh man, that really threw me for a loop, dude. I
Think
can't.
spectroscopy and then think interferometry, and then you just got to take the first half of one and the second half of the other.
Spectrometry.
Holy crap, dude.
Yeah.
I can't do it.
Me neither.
I just failed by myself miserably 4 times. Thought I tell you? You know what?
That's hilarious.
She soars by the spectrometer. All right. So there are many variations of mass spectrometers, but all of them are based on the Lorentz force law, which is F equals Q times E plus V times B. The earliest usually relying on the deflectors of a moving charged particle in a magnetic field. If there is a region in a vacuum with a uniform magnetic field B and a charged particle or an ion is ejected perpendicular to the magnetic field, the particle will trace a circular path where the plane of the circle is perpendicular to B. The equation of motion is noted here in equation 1. where Q and M being the charge and the mass of the particle, tracing the circular path of the radius r, and the quantities on this RHS of this. I'm sorry, and the quantities on this RHS of this equation are known. All right hand side. Then the charge mass ratio of the particle would be found. The general particle trace only parts of an arc would then leave the magnetic field and travel straight hitting the screen. In the early days, a photographic plate was used. Second, I'm gonna grab a water. Some reading water, as they say.
Cool.
All right. Let's see here. All right, where were we at? The deflections.
By noting the position that the particles hit the screen. So it's like the second sentence there.
I see. By noting the position that the particles hits the screen, and together with the measured deflections of the particles' direction from its original direction, the radius r could be found. Wait. Oh, for its deflection orbit, or for the radius of the charged particle. By noting the position
the path of the particles. Sure. Yes, there's an R in the change of direction.
I'm sorry, say that again, Stone.
Because it hits the B field.
So this is them
firing this particle at the B field, and its change in direction is measured in terms of its R.
Right. So they're saying that based on that deflection angle, they're
just how far it deflects and what that total shape moves.
Gotcha. Okay.
Yeah, they're guessing mass by how far it deflects. Yeah.
Yeah, essentially. So yeah, this is very reminiscent of this real quick. Let me bring this up. This is exactly how they came up with
like
with the electron. Or whatever, or summit, or history toroidal. Yeah, this is what
firing a particle. Really, all they're coming down to again is the smallest integer, right? What is the lowest energy state that matter can be at that they can still measure it? That has an energy state above zero, and they're going to fire that quantity of energy and call it a particle.
My man, dude. Straight facts. So that's exactly what they did with J.J. Thomson and the cathode ray. This is where they derived the mass exactly by the method in which this dude's talking about here. And once they had that, they just distributed that low energy state. So that lowest amount of energy that they could measure in a system and like get a change, they defined that amount of energy as the electron. So everything based off of the atomic model and all that is all measured in relation to this, or to the mass of the electron. And it was derived exactly how Stone just described it.
For sensitivity.
Yep, dude, exactly, dude. That's why when they got the muon and stuff, they're like, "Oh no, this is like a lower energy state that we can only measure like fluctuations as it goes in and out." So like they can't ignore it, but like that's how they incorporate this stuff. It's all energy fluctuations.
You got it. Yep.
Well said.
And sensitivity goes up, and particle size quote goes down.
Dude, all of a sudden there's a new particle on the streets, bro. Oh my god, that's beautiful.
Like, yeah, man.
Yep. All right, cool. So I was wondering how they came up with R for when I was looking into the cathode ray stuff, and yeah, that makes sense. So because once they have the energy input and the radius, they use their coefficient to distribute that over it.
That dotted line right there.
Yep, and then that gives them
the line is curved, and the R center is top left.
Wow, perfect, dude. So that's how they did it. Yep, and then they literally based everything off of this experiment. J.J. Thomson, what year was that? Let me get you the exact year. J.J. Thomson, 1897 cathode rays. So this is what made him go towards the atomic model and like view it as correct and whatnot because of this experiment and how he derived it. Because he was actually working on his own ether vortex theory, so he conceptualized the structure of matter being little vortexes within vortexes, essentially. But the math wasn't sufficient to describe that interaction yet completely. And this is super convincing, right? Like they applied all their known mathematics to it, all the ways that they could do to like derive mass out of this, to attribute mass. They did it and it deflects, and they're like, okay, well, it must be, it must weigh this much. It must be this radius. It's awesome.
Well, hey, if you were born 160 years ago, you'd be convinced looking at that thing, wouldn't you?
Oh, 100%, bro. I don't when I was doing the history of this, like, and like actually going over, like, you put yourself in the mindset of people that just discovered like radiation and all this and like the different waves within radiation, so gamma rays, alpha waves, beta waves. And it's like you don't know what's going on, dog. You're deflecting this thing in a tube, and you're like, well, if I apply this math, I mean, I don't know, is it a particle? Like who, you know? It's all very like in the moment I could see how it would be how you would believe in it, based off of certain things like that. Because then you could be like, well, I predict that based off of this mass, it'll deflect by this much when I introduce this electric current, right? And then
Well,
you
and
get that deflection,
I
and you're
like
like, there you go.
I like his spring analogy too, right? It's like, yeah, you could make a spring like a spring scale, and within like a certain area, like a certain level of what's the word? Like a certain level of measure, like a certain area of measure, it'll be accurate. But like we all know, eventually it's not perfectly linear if you're going to use a spring to measure something. Like there's going to be a point at which it's going to drop off in its tension or increase in its tension, in a way that's not perfectly linear.
Mm.
And like that's kind of like
So
you're making an
this is a
assumption.
divergence again. Sorry, go ahead.
What's that?
Go right ahead. I'll finish when you.
No, that was pretty much it. It's just it's like the idea being that just because you've measured one thing here, like you can't make the assumption. You're making a big assumption that everything is going to hold consistently with all your measurements using this method.
I'm
I
seeing the
guess.
divergence yet again between kinematics and dynamics here that they analyze really good, but just assigning cause and coming to conclusion, it's swing and a miss all the time.
Yeah.
I mean, appreciate maybe that they did actually break ground here, but just not in the way they want us to understand it.
Mm,
Maybe all they really did in the sense of the integer of the situation here, in terms of energy increment and deflection element element, is that they have correctly described the ratio between the masses themselves, with the lowest common denominator being hydrogen. But they didn't prove anything beyond that. That it is the lowest common denominator. That's not what they proved. All they did was prove ratio, and they mathematically pin the reference point on hydrogen.
hmm.
You know what I mean? Did everybody get that, or should I
Break
say
it
it again? Because this is
break it
actually
down.
a fine line,
Break it
but
down
it's a
again.
good point. Okay, back to the beginning. This is where the divergence occurs between kinematics and dynamics with mainstream physics all the time. They get the analysis right, but they get the reasons wrong. They get the conclusions wrong. This test is valid in that they're using a piece of energy X size, but the point is that that size is not the smallest size possible, which we found as we continue down the timeline. And they got more sensitive apparatus, and they can use smaller quantities of energy. And then they call them subatomic because they're giving this guy all the credit for something he shouldn't get credit for. Not far. He should only get credit that he's established an integer like relationship slash ratio between the masses of the elements. But hydrogen isn't actually 1 compared to 0. You know what I mean? Maybe that's 800. We can't see it because it's so bloody small. And that at the time, we weren't able to fire fewer than 800 of them at a time through the tube. You know what I mean? That what we're doing here is we're establishing the ratio of masses, and that there's 16 of masses of this same size that is hydrogen. There's 16 times as much mass
Mm.
in oxygen.
So you're just
so to
you're
speak,
saying everything
right?
is
But
quantized
it's
to
not that
that.
one is the lowest number. It's quantified,
Oh,
quantized,
okay.
right? It's all ratioed against the lowest common denominator, which was hydrogen, and they gave that the number 1.
Right. Okay.
So it's
So
one of these and 16 of those.
got you. So this is analogous to what they did with the electron.
And yeah, so you'd need 16 hydrogen thingies
Right.
fired at the deflection plate, and it would go with the same radius as one oxygen thingy. You'd have the same R.
Right. Once they can attach one thing to it, they could reverse engineer everything back off of that and use the original thing to reify it. Right.
Yeah, they took the smallest reading they could make,
Yep.
attributed that to hydrogen, and declared that value 1.
Got you. Okay. Yeah.
And then they extrapolated everything else in terms of ratio from there.
Yep.
That's how they did
Okay.
it. Sleight of hand, bro. It's all in the math.
Oh, thank you. Thank you. Dude, that's how they do. Oh, that's so ah
It's sleazy.
dude, it's
So although they've gotten a higher level of precision with their measurements now, they're still working within the framework of the periodic table and atomic masses and
that
based
original
around
setup.
those initially quantized values, right? Is that what you would say, Stone?
You got it. Because nobody would dare to change the numbers on the
Mm.
table.
Mm.
That would be heresy.
Dude, you can't do it. You gotta look at those deflection or what are the defect value, the defect masses. You just gotta look at them and stare. You can't
Those
touch them.
defect
You can't touch them, bro. You just gotta look at that violation of mass conservation, bro, and just eat it and just be like, I totally am super into this. This is my favorite type of framework of
Yum 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 yum. Chip sandwich. I love it.
Eventually, you just become the guy at LIGO that didn't even believe the thing he spent his whole life looking for.
He's like, dude, they detected it. Are you super pumped? No, I couldn't I couldn't care less. These youngsters will learn soon.
The video is everything about current physics.
Yeah.
Well,
All right.
let's knock this out. Want me to take over again, or?
Yeah, sure. Yeah, I gotta go.
So
To the
we're
bathroom.
on the where were we exactly?
So we're
Are we at
right. We're right around. Let's see.
Charge queue.
Thank you. Okay, I'll start from
Yeah,
right
the
there.
charge queue. All right, I'll be right back. I gotta go to the bathroom.
Cool, go for it. The charge queue is usually one electron charge. In this manner, the mass could be found from the equation 1 above. The Penning trap makes use of the same uniform magnetic field to trap an ion in a circulatory motion in the xy plane about a z-axis parallel to B. Such a pure circular motion in the xy plane cannot be stable. The Penning trap makes use of an overlap of a weak static and an alternating voltage across the z direction to restrain the motion of an ion along the z axis. In this way, the ion is trapped in a 3D oscillatory motion within a cell space. With proper choices of parameters for the electric and magnetic fields, an ion may be trapped within a cell with a typical dimension of 1 centimeter to 5 centimeters. At present, nearly all nucleic mass measurements are made with the Penning trap, and the resolution may go as high as 1 part in 10 to the 11th power.
Which is
For the
100 billion.
Cool. So from the same equation of motion 1, we can arrive at an equation with an angular frequency WC instead. M equals QB over WC. With the same unchanged electric and magnetic fields environment of the trap for two particles, the relative mass of two masses M2, M1 with the same electron charge would be M2 over M1 equals W1 over W2.
Little omega.
Oh, thank you. So M2 over M1 equals omega 1 over omega 2. So the ions trapped in a oscillatory motion within a cell space. So the z-axis, I mean, just as I'm thinking about this, like it seems quite presumptuous. Like, how are they not? Or I guess I would have to look a little closer at their math, but I would assume you would lose some energy on those z-axis motions, and then just in general, like losing energy. I don't know. This is a new topic to me, but
I
I
think
can
the z
see.
vector changes as deflection occurs across either the x or the y. Both is going to be the again. This is a spherical geometric calculation where because the line is bending, you're going to lose some of your forward z.
Okay, but that's
That's a longitudinal reduction. It's incredibly small ratio.
gotcha. Oh yeah, so let's go ahead. We're below equation 3 there now, Alan.
Alrighty.
This equation, or go back up a little bit. There we go. This equation is only a simplification to show that the relative atomic mass is related to the ratio of characteristic frequencies of trapped ions. Actual relationship is complex. The Penning trap enables a measurement of relative frequencies to arrive at a relative atomic mass of two ions trapped under the same trap parameters. It is the very high resolution with which the frequencies can be measured that the Penning trap can measure relative atomic mass to the current high resolutions. Wait, what? It is the very high resolution with which the frequencies can be measured. Okay, so it's because they can measure the frequencies at such high resolution that they say that they can measure the atomic mass with high resolution. Ah.
The
Okay.
old switcherooski, bro. That's literally welcome to Compton, bro. Straight out of Compton effect.
Dude, yeah, that's crazy. And if that's off, there's just a mass defect, and don't worry about it because like we do know for sure that that frequency resolution is really high. So just be impressed with that and stop asking questions.
Nice.
Lorentz force law unverified. First and foremost, the Lorentz force law has not been experimentally verified directly. Mass spectrometry makes use of F equals Q times V times B when used to implement a measuring technique. The precision of the technique cannot be higher than the precision to which the law has been verified experimentally.
Oh, well, hello there.
Common sense, come on now. In order that
Little snafu, hey boys.
In order that mass spectrometry can measure atomic mass 1 part to 10 to the 11th power, how much was that again? A billion?
One
100 billion?
parts
Is that what
in
you
the
said?
1 in
millions.
100 billion.
There we go. The magnetic force law 2 need to be experimentally verified to at least this
Yeah,
order of precision. But the Lorentz force law has never been directly verified through experiments to be correct as a mathematical law expression. In schools, the Lorentz magnetic force law is only demonstrated by showing how a magnet could deflect an electron beam in a discharge tube, but this is not the type of verification that would suffice for the Lorentz magnetic force to be the basis of a technique to weigh atoms.
No way, dude. Oh, no way they do that. And then they just mathematically extrapolate it out to the infinitesimal approximations down to the, what was it, Stone? 100 billionths, trillionths of a zillionth?
Yep.
Or was that 1/16 billionth of a zillionth? That's
Dude, so just think about how you show this paper to somebody like a Glober, and they're gonna give you so much crap about how this isn't peer reviewed and this guy is a factory worker. And this factory worker is just dunking all over them, like, so hard. Like, this paper alone is, like should be enough reason for somebody to just, like, throw out all credentialism. This is, like This guy is a very good writer, and he's making very, very solid, substanceful points or substantial points. But anyways, Lorentz magnetic force to be the basis of technique-weight atoms. There has also claimed Lorentz magnetic force has been individually verified by the force between current carrying conductors. This too is insufficient. It is not a general verification, as we know the drift velocity of electrons within conductor currents is in the order of millimeter per second, whereas the velocity of the ions are moving way beyond such velocities and also in vacuum. If we ponder the question in some depth, we may arrive at the conclusion that there may not be any means to verify the magnetic force law directly. It would require the need to measure a magnetic force acting on an infinitesimally small moving particle in a magnetic field. Just measuring the force itself would present an insurmountable obstacle. Magnetism is founded on the Biot-Savart law. It implies measuring the magnetic field B of the Biot-Savart law precisely and without recourse to the Lorentz force law itself. It is unlikely that any physicist would be up to such a task. This may be the very reason why no experiment has ever been done to verify the Lorentz force law to any degree of precision. Man, it sounds so familiar. Without the Lorentz force law being verified, other methods have to be found to be directly verify the technique of mass spectrometry itself. The relativistic mass effect. The relativistic mass, or the relative mass between two ions in mass spectrometry, is strictly the ratio of two relativistic masses. There shouldn't be a further gamma factor to each of the masses, giving the true rest mass ratio of m1 over m2, an additional relativistic error proportional to gamma 2 over gamma 1. The two tables 1 and 2 show the estimates. The simplified formula for the velocity of an ion with a penning trap is V equals Q over M RB, assuming a small v over c. Increasing magnetic field will allow for cells of smaller sizes. Typical values of B ranges from 3 to 9T. The cell and dimension ranges around 1 to 5 centimeters. The gamma 1 over gamma
Let's see
2
here.
error. What's that?
Teslas. Sorry.
Oh, gotcha. Okay, thank you. So
Sorry.
typical values
3 to
of
9
B ranges
Teslas.
from
Yeah.
3 to 9 Teslas. Okay. The cell dimension ranges from around 1 to 5 centimeters. The gamma 1 over gamma 2 error increases with increasing radius r and b. As seen from the pair C12 over, slash H1 for r equals 5 centimeters and b equals 7 Teslas, the relativistic error factor is about 6 part in 1,000. If such high systematic error or systemic errors are found in mass spectrometry, then it is truly unreliable. With the typical parameters as in the tables, it is not possible for the penning trap to determine the mass of electron or the mass of the electron if paired with C12. The very small mass of the electron would need near light speed for it to stay within the penning trap. So they couldn't experimentally verify it if they wanted to. Their precision. Is that what I'm reading there?
Yeah, if we're trying to verify relativistic mass.
That's always cool.
Yeah.
It's all right. We'll just reify it anyways. Ever since the invention of mass
Hey,
spectrometry,
we have no degree of precision for the Lorentz force, but we're going to go ahead and build an entire measurement system based on that to reify.
We'll just reify it on the back end like everything else.
Dude, I'm excited to talk to Franco again. We've got some ammo
Oh,
for
fuck
him.
that guy, dude.
Oh, Franco, yeah, he's muted on Twitter, but if he ever
Yeah, for
shows up on a
sure.
if he ever shows up on a Flat Earth Friday again, man, I want to ask him about mass spectrometry and how it's been meaningfully
Dude, he'll just
substantiated
tell
to
you
have the
that you're
precision they
stupid
say it
and then
does.
to read Wikipedia 19 times in a row. So I don't know. Or whatever.
All right. Well, let's keep going here.
So, yeah. Mass spectrometry may not be an accurate technique to measure atomic masses of elements. Even though the resolving powers and precision of the penning trap may reach 1 part in 10 to the 11th, such a precision does not translate to accurate measured values for atomic masses if the principle behind mass spectrometry itself is inaccurate. It may even be possible that the systemic error of mass spectrometry renders its accuracy to only about 1 part in 10 to the fourth power, a 7-order difference from its precision. It is conceivable as precision and accuracy are two fundamentally different aspects. As long as mass spectrometry is not verified, its accuracy could be anything. The accuracy of mass spectrometry is unknown as it has not been verified. Wow. As we have seen earlier, all our balances for what's up?
So when they say seventh order there, they mean 1 in 10 million? 1/10 millionth of the precision they think they have? A 10 to the 11th, when they come down to 10 to the 4th, it's 1/10 millionth of that precision.
Thank you for that. That's a good point. Well, why don't you just let them be excited for a little bit? As we have seen earlier, all our balances for weighing macroscopic mass have been validated to be reliable in principle. As to what precision the balances could deliver, a matter of design and technology. On the other hand, atomic mass is now solely determined with mass spectrometry, but its method is unverified. G. Audi in Citation 1 described in The History of Nucleic Masses and Their Evaluation how, with his improved mass spectrometer, Francis William Aston in 1919 could revive the whole number rule of atomic weights. The only exception seems to be hydrogen with an atomic weight of 1.008 in agreement with the value of the chemist. There was a discrepancy in the weights of helium and hydrogen from the whole number rule. The atomic weight 4 of helium was short of the weight of 4 hydrogen atoms. A mass defect was discovered. It was Arthur Stanley Eddington who observed the famous solar eclipse of 1919. Dude, he knows. Who accepted the discrepancy of the atomic weights from whole numbers as correct, as he proposed the notion of a mass defect with the mass energy equivalence of equals mc squared to account for the source of the sun's energy.
No
This theory
way. They turned their air into the proof of their model. Dude, shout out to Eddington, bro.
right,
That's legendary.
Can I
He's an impressive guy.
can
What's
I
up?
bring you guys back to a figure used earlier in this paper and relate it to what he's saying here? That when they
Absolutely.
were talking earlier about that discrepancy of 0.000012, you guys remember that number from back?
Mm-hmm.
That's how far off they were in the assessment of a particular weight away from its supposed integer value, which is the defected ratio.
Yes.
Well, actually, what you're looking at there is essentially, as far as they are able to measure, the actual coefficient we should be applying to the number 1 when we talk about hydrogen. That 0.000012 is 12 parts per million, or 12 in a million, if you want to think of it that way. That's really what they were or measuring when they hit number 1, was the inverse of that. That it's not really 1 between this one and the next one. It's the inverse of 12 in a million between this one and the next one. And that's how many, what's the word? Divisions between the two supposed whole numbers they're measuring currently at this level of technology. That's suggestive mathematically of the real smallest quantity of energy. That it's actually 12 in a million of what we're counting as 1, if you guys can see that ratio. There is a mathematical implication here in their own error, their own defect, and the way they quantify it.
So like
I hope that makes sense.
is hydrogen, or is hydrogen not non-whole number? Is it the only one that's non-whole number?
I'm saying that whole number should be broken up into a million, and perhaps as few as 12 out of that million is actually the value 1. These whole numbers are actually much gigantically larger numbers and
Stone.
ratios of each other on that mathematical basis.
So you're saying
That ratio.
okay, so when you said that on the inverse, That the thing that they've constructed is actually significantly larger than what it should be for it to even be 1. For them to even get a whole number.
It should be 12 in a million of the 1. That if 1, you change that, all of a sudden that value is a million. The smallest energy unit isn't a million, it's actually 12.
The smallest energy unit based on the smallest mass unit.
Right. Right. That the value of hydrogen isn't 1.008 or any such fiction. It's nowhere near 1 according to that metric of minimal irreducible minimum energy unit that they're firing across the plate in one burst of energy, right?
I mean,
That is the inverse of 12 parts per million in terms of lowest common denominator instead of 1.
my question is if an atomic mass unit, right, of hydrogen is 1.008 and they're building everything off hydrogen, why would they not redefine it to be an atomic mass unit of 1? Like, where's the 0.08 come? What does that make an atomic mass unit then?
It's because you can't multiply 1.008 times 236 to get the first uranium on the scale, 239 or whatever number your favorite number for uranium is.
So it's
Wait,
just
so they're
You know what I mean?
saying uranium is more
The-
important than hydrogen?
That 0.008, when you have 239 of those leftovers, it's not going to.
you're cutting out real
saying
bad all of a sudden,
math-
Stone.
Oh God, I'm sorry, guys. It's living in Uruguay. Am I cleaned up?
Yeah.
Yep.
It's about how they're slicing it. It's that they need to slice it 12 parts per million finer than just the integer 1 in order to even represent hydrogen in a simplistic way, right? That they're actually showing you the degree to which it should be quantified, nowhere near whole numbers and the ones that they're using with the relative masses that they are on the chart, on the table. But it didn't hurt your brains too hard, but that's that's what I noticed in terms of this implication here. Oh, defect.
So the defect is what the hydrogen would actually be. And they include that in the 1 because they need it to do, to basically make up the molecular structure of everything else.
Yeah, so out of 1, whatever you want to assume that amount of mass is, hydrogen is actually 0.000012. It's not 1.
Right.
They're calling it 1, and all the rest of them are ratioed off of the number 1 instead of 0.000012. Which, again, how are they measuring to do the millionth of an atomic mass?
Where
With
does the
any
1,
kind
2
of
come from?
precision,
Where do we get that
It's
number?
earlier in this paper.
Oh.
Yep.
It's earlier in this paper when they deal with the figures, like you can see currently at the top of the view, where it talks about the weight of 1.008 of hydrogen. That it's not even that they start to show numbers that are 11 digits to the right of the decimal place in terms of precision of the measurement, right? And then they cut it back to 6, and then they come up with this figure 0.000012 in terms of a quantified error, defect, whatever you want to call it. What they're really doing is they're implicating themselves in terms of their resolutive capabilities in measurement.
It's absolutely absurd that they would say that our measuring device is so accurate that it can not only measure what it is, it can measure what it should be. We know what the weight of an atom should be, and all atoms are defective. That's like retarded.
Anything that doesn't fit the whole number is a defect because it doesn't fit our rule.
Not
We
only
quantified it 128 years ago.
Ugh.
Cool. Yeah. So let's knock this out then.
Yep, cool. All right, so let's see.
We're on that bold sentence there, aren't we?
Let's see. Yep. Mass spectrum. Man, got me again. Mass spectrometer. Mass
Spectrometry.
spectrometry.
You have to say it without thinking.
Next,
Yeah,
yeah,
just
dude,
phonex without thinking what it means.
that's exactly it. You can't think about it. You just got to commit. Mass spectrum. Damn it, psyched myself out. All right. The mass of this word was only an approximate technique.
That's for the
Mass
first. That's for the
mass
next word.
spectrometry. Yeah,
There you go. Boom.
may not be. I did it without thinking. You almost psyched me out though. May not be an accurate way of measuring or weighing be an accurate weighing technique. This is not surprising as it was not verified. It is conceivable that if we had weighed atoms using a beam balance, the atomic weights would be just whole numbers equal to the mass of the nucleotide of the atomic mass unit. Yeah, indubitably. This hypothesis is not outrageous. It is just the law of mass conservation at work. We know that the free neutron decays into a proton and the electron with mass conservation. The mass of the neutron is simply the sum of the mass of the proton and the electron. This is also the mass of the hydrogen atom. Also, with the law of conservation with the mass of the nucleotide, just as the mass number and the atomic mass unit, if the law of mass conservation is found to be correct, the implication would be unimaginable. Wait, did I read that right? Yeah. If the mass conservation is found to be correct, the implication would be unimaginable. There would be no need for the laws of mass energy conservation, no more mass deficit, and using the equation E equals mc squared, there would be no need to weigh atoms. But one very important theory would be missing, the theory of nuclear energy. We would have to come out with a new theory to explain nuclear fission and fusion. If the law of conservation of mass is incorrect, it would mean the total collapse of nuclear physics as a theory. Sodium fluoride holds the key. As we have seen so far, the very fate of physics depends on the answer to just one question. Is mass spectrometry, man, added a different letter there. Is mass spectrometry,
Sorry.
You nailed it. It's on fine.
wait, no, I added a P. Did you hear that? Spectrometry? That's not a word, bro. I just psyched you guys out. Oh, that's not a word. Is mass
So entertaining.
is mass spectrometry is mass spectrometry reliable? We already have some views on this question. Firstly, the Lorentz magnetic force underlying the mass spectrometry has not been verified. Secondly, mass spectrometry fails the linearity test. The atomic mass of the helium-4 is 4.002603 AMU. That of deuterium is 2.014101 AMU. We know that helium-4 has exactly twice the number of electrons, protons, and neutrons as in deuterium, but the atomic mass of helium-4 is not exactly twice that of deuterium. GG. All right. The notion that mass spectrometry weighs atomic mass is only approximately. The notion that mass spectrometry weighs atomic masses only
Start the
approximately.
sentence up a line. But the
Oh
physics
yeah, yeah.
prefers the
Sorry, thank you. Oh, I over highlighted that.
Yeah. You think you? Yeah.
Okay, there we go. That was the twice of the deuterium? Thank you. Okay, but the physics world prefers the concept of mass deficit and the rejection of the notion of mass spectrometry weighs atomic masses only approximately. So they reject that notion and they accept the old deficit. That's cool. Such is still just an accepted viewpoint without any experimental justification. But there is one way to resolve this question conclusively and also very easily. The key is found in sodium fluoride, NaF. We finally have to do some consistency test. We finally have to do a consistency test for mass spectrometry. The mass spectrometry is not the only technique available to weigh atoms. The chemists of the 19th century already had done that. The atomic weights in chemistry in earlier centuries are actual chemical analysis of compounds, and the weights are determined with the chemical balance. Oh, the old measuring, like the old way, right? The old balance.
Empirical method.
Yeah, that's the word I was looking for. Thank you. Okay, a direct method of weighing, yeah, the direct method of weighing the mass. They had a value for the relative atomic mass of the pair of over F. The 1900 value of the atomic weights of chemistry of Na is, what is that? Is Na sodium, right? Sodium
Yeah.
is 23. If F is 19.03, or that of F is 19.03, this gives the relative atomic mass of sodium to the fluoride to be 23 over 19.03 or 1.21. This is because it happens that sodium and fluoride both occur in nature as the only stable isotopes, but this figure of 1.21 is of insufficient precision to decide the accuracy of mass spectrometry. The relative atomic mass of sodium over fluoride, based on the current atomic mass, is with the deficits or whatever. So then it comes out to being 1.210089. This figure may be taken without uncertainty, as the atomic masses have no uncertainty in the sixth decimal. The ratio of the mass number in F is 23 over 19 or 1.210526. So the problem reduces to doing the chemical analysis using our chemical balance to determine the relative atomic mass of Na over F, whether it agrees with the analysis using the deficit or the other one. To conclusively resolve the question of reliability of the mass spectrometer, we need a figure that is at least accurate to the fourth decimal place, i.e., 1 part in the 10 to the fourth. Fortunately, the current analytical balance has a precision of 1 to the nice of the 1 part 10 to the 10 to the fifth, or even higher. With a fresh analysis of NAF, today we could come out with a value of 1.210089 plus or minus 0.00000012, confirming the accuracy of mass spectrometry, or the value would be plus or minus that, rejecting it, confirming the law of mass conservation unequivocally, and rejecting the what is it, relativistic energy equals mc squared or whatever, relativistic mass.
Well, there's that famous number. Oh, 1, 2.
Yeah,
Also wanted to come way out of left
yeah,
field for a second, regarding 23 over 19, this mass ratio between sodium and fluorine.
yeah.
You guys remember the movie Monsters Inc. Disney production?
I
It's the
mean,
one
I'm
that
Yeah.
aware of
movie
I'm
that
aware of it.
2319.
children's got the monsters under the bed, and that's how
Right.
they get the energy for their civilization and stuff. Do you guys remember the code number for when a monster comes back infected with a piece of human stuff on them, like a sock on the guy's shoulder when he comes back through the door? What's the code?
I have no idea.
2319.
2319. Yeah.
2319! 2319! And all the sirens go off and they hose the guy down and they sterilize him and burn all his fur and singe him to a crisp so that he's not infected by that sock anymore. Yeah, that was code 2319.
Huh.
Just for trivia's sake. It just struck me really hard when I first saw that. Anyways,
Yeah.
Sodium fluoride's
there's
also what they put in everybody's water to
No,
sterilize
di-
them.
isn't it a
Their
difference?
brains.
there's
thing?
the 001 that's the implication right there. They're saying that there's an error of give or take that, when that is very well could be the smallest order of magnitude when you're talking about something like hydrogen.
Hmm.
That could be the smallest recordable value right there. Their error. You know what I mean? We're simply addressing that Oh no, it's not just a whole one anymore. It's quadruple O 1 2 to the right of the decimal point. 12 parts in a million instead of just one. That it's right there. And again, I think that number over time is going to change as technology advances even farther. And it's going to be 8 or 9 or 10 decimal places of error. And then we're going to have to readjust our assumption about the smallest energy unit of what we can find in a chunk of hydrogen, for example. Anyways, go on.
Well, thank you. All right, so we're about to wrap up here. Let's see. The question of the accuracy of mass spectrometry could be resolved conclusively by chemical analysis of sodium fluoride to determine the relative atomic mass of Na over F. If the figure matches the approximations before they made all the weird changes, then it would mean that the laws of mass conservation are confirmed and the relativistic explanation that they give would collapse, and we would have to redefine how we talk about nuclear physics. All right, cool. Conclusion. Mass spectrometry has achieved a very high precision, even reaching 1 part in 10 to the 11th, but the precision and accuracy are two independent aspects. Until now, there have been no experiments done to verify the accuracy and the reliability of the technique of weigh atomic masses. The current accepted mass of nucleotides published in the CODATA with the precision of reaching 10 to the minus 10 may even be just as accurate as only 10 to the minus 4. Can you imagine thinking that you're accurate 10 to the minus 10 and you're only accurate 10 to the minus 4? That's so embarrassing.
1 million.
I would kill myself. Yeah.
1
Absolute-
millionth of the accuracy.
Dude,
Yeah.
absolute noob. All right. Of the orders of magnitude, let's see, off by 6 orders of magnitude. If atoms could be weighed with our verified chemical balance, the atomic masses of the nucleotides may just be the mass number in the unified atomic mass unit. This would mean that this would be a confirmation of the conservation laws for mass in the atomic within the atomic and subatomic world. Whether mass spectrometry is consistent with our analysis or with our analytical balance of weighing the masses could be tested through chemical analysis of the sodium fluoride to be determined that the relative atomic mass of the sodium fluoride is ratios proportional or whatever weighs the same, and the accuracy of mass spectrometry would be confirmed to that order of magnitude plus or minus 0.0000112, which may or may not be what hydrogen is to begin with. Otherwise, if the value is 1.120526 or plus or minus the other value mentioned where it was 0.0000012, it would mean that the mass conservation is upheld, and the latter outcome would mean the total collapse of nuclear physics theory, and we would need to develop a new theory for nuclear physics. All right. Shout out to you, boy.
I have a
Boom.
question.
What
What are
up?
the odds? What are the odds that this random guy who's a factory worker with no education, who's written all these papers, is not actually like a ghostwriter, and he's actually some scientist somewhere who doesn't want his real name known so he doesn't destroy his career?
I mean, it seems
I'd like to think he's
I
just
have,
a
no, I
humble
have no
factory
problem
worker.
with him being a factory worker that figured it all out, dude.
Yep.
It actually, to me, makes the most sense that way because he's not indoctrinated.
Yeah.
Not to
Ooh.
say, not to say you can't get valuable education from school. Obviously, you can, and you can avoid the indoctrination. I think you're going to be able to pull it off. But just in general, to have someone have such a cutting criticism of it, like it kind of seems like they had to figure things out outside of the system.
To reference Malcolm Gladwell, I'd say this guy put in his 10,000 hours.
I missed the first part of this paper. The nuclear bonding energy fails. Like, what was the in the first half of the paper? What was the criticism of it? Like, what's the failure part? It's in like a 30-second summary.
Making a relativistic measurement instead of an empirical one.
Yeah, but like he's proposing an experiment where we could verify the ratio of sodium and fluorine, but I'm talking about like he's talking about the nuclear bonding energy like measurement failing, and there's like a table. What was the first half about?
As far back as I can remember, it was just about the additive mass of the
Yeah, I'm a
commutative
little
formulas versus the two constituents weighed separately.
we just went through his webpage and 3 papers, so
Toby says my brain is fried.
yeah, I can't necessarily remember which paper said what
The
exactly.
one that the most recent one, but it's okay.
I'm so excited. Like all 3 of those papers were definitely indicative that it's going to be worth it to read the rest of them.
They were an indictment.
They were all 3 of them, one after another.
Well, the experiments still need to be done, though. I mean, I wonder if you could look up any Google Scholar or other resources about like chemical balance analysis of pure distilled water.
Yeah, you absolutely could.
And see if there's someone who's done it already and which one it comports with.
Well, cool. I'm not even streaming, Alan. So whenever you're ready to wrap up your stream, we can go ahead and close it out, and then I'm just gonna mirror yours whenever it's done.
All right, cool. Yeah, we'll go ahead and close it out now. Was there any final thoughts or anything?
Einstein's a big old gay
Yeah, I
boy.
want my money back.
No refunds. All right. Thank you guys for coming out. Catch us tomorrow on Flat Earth Friday. I think Shane is going to be co-hosting. If
Am I? Okay, cool.
I don't know, are you?
Wait, I didn't know that sacred. Yeah, maybe I'm down.
Yeah. Anyway, someone will be definitely co-hosting at tomorrow. Like, So anyway, catch us tomorrow at 8 p.m. Eastern. We'll be live for Flat Earth Fridays. Peace. Oh, and then Tuesday, we'll be taking a closer look at quantum electrodynamics. We'll be diving in deep in there and looking to see if we can find the proofs there, right? The proof is in the pudding, and we're going to see if we can find pudding or whatever that we're